Welcome back to the today's class. Today we will be seeing about DC circuits and the problems related with the DC circuit and some reduction techniques used in star delta conversion also we will be seeing in this problem. First problem, three loads A, B and C are connected in parallel across a 250 volt source. Load A takes 50 amps. Load B is a resistor of 50 ohms and load C takes 6.25 kilowatt. Calculate the following. Load resistance RA and RC, the current through load IB and IC, power in load A and B, total current delivered to the load, total power delivered to the load, total effective resistance. So, on reading this problem, you can see there are three loads, load A, load B and load C. These three loads are connected in parallel across a 250 volt supply. Here, the load A takes a current of 50 ampere. This is the load A and this load takes a current of 50 ampere. Load B is a resistance of 10 ohm. So load B has a resistance of 10 ohm and load C takes 6.25 kilowatt. So this one is the load C and this resistance has a power drop of 6.25 kilowatt. You need to find the load resistance across RA and RC, first one. Second, you are going to find the current through IB and IC, that is the resistance B and the resistance C. Current flowing through load B and the current flowing through load C. Next, power in load A and B. So the power which is absorbed by the load A and B you have to find. Next, total current delivered to the load. So the total amount of current flowing to the total load, that is load A, load B and load C. Next, total power absorbed from the source, that is the total power delivered by the source. Then the total effective resistance of the load. So the given data are the voltage source rating is 250 volt, load A current is 50 ampere, load B resistance is 10 ohm, load C power is 6.25 kilowatt. Load resistance RA is equal to B by IA. So this one is the load resistance. So you need to find the resistance. Here we can use the Ohm's law. So RA is equal to V divided by IA. Here the V is known, which is 250 volt, and the current through the load resistance A is 50 ampere. So we will get 5 ohms as load resistance RA. Next, load resistance RC. Here this one is the load resistance RC. Here you can see that the power absorbed by the load is given as 6.25 kilowatt. So you can use the same Ohm's law and substitute V is equal to I is equal to V by R, and you can derive to this formula. Here you can see RC is equal to V square by PC. Here C is denotes the power absorbed by the load resistance C. So V square is nothing but 250 whole square divided by the power absorbed by the load C resistance is 6.25 kilowatt. So 250 whole square divided by 6.25 into 1000. To convert kilowatt into watt, you have to multiply it by 1000. So the answer is 10 ohm. Next, current through resistance B, that is the load resistance B, is IB, and you can find it through Ohm's law. B divided by RB. Here the voltage is known, which is 250 volt, and RB is 10. then you get 25 amperes of current will be flowing through the load resistance B. Next, the current through RC is IC divided by IC is equal to VC divided by RC. So 250 divided by 10, again it will give 25 amperes. Next, the power drop across RA is PA. So the power drop across the load resistance A is denoted as PA, and it is V into IA. Here you know V is 250 volt and the current is 50 amperes. Then the power drop is 12,500 watt, which is nothing but 12.5 kilowatt. So the drop across the resistance B is PB, and here V into IB, the voltage is 250 and the current is 25 amperes. So you will get a power drop of 6.25 kilowatt. Next you are going to find the total current. So total current I is equal to IA plus IB plus IC. Here you need to add the three currents. So the total current which is flowing through this line will be divided into three parts, one for IA and the other for IB and the other for IC. So to find the total current I, you need to add all the currents through IA, IB and IC. So this will give you 50 plus 25 plus 25, which will be equivalent to 100 amperes of current is delivered to the load. Next, the total power is P is equal to PA plus PB plus PC. Here the PA is 12.5 and PB is 6.25 and PC is also 6.25. So all these are calculated and PC is given, so you can substitute all the values and you can get the total power delivered by the source is 25 kilowatt. The last one is the total effective resistance. Since all the resistance are in parallel, you can find it by using the formula 1 by Ra plus 1 by Rb plus 1 by Rc whole inverse. So you can substitute all the values and you can get the value as 2.5 ohms. Second problem, using star to delta conversion technique, obtain effective resistance across AB for the given figure. Here the outer circuit is delta and the inner circuit is star. So first you are going to convert this star connection into a delta connection. Then you are going to apply the transformation rule and you can find the effective resistance across AB. So first we are going to convert the inner star connected circuit, that is 3 ohm, 2 ohm and 6 ohm, into delta connected circuit. So redraw the circuit, that is the inner star, like this, which is 3 ohm, 6 ohm and 2 ohm. Next we are going to convert this inner star into delta like this. So first we are going to find the resistance RAB. To find this, the formula is RAB plus RC divided by RC. Substitute all the values. You know RA is 3 ohm, RB is 2 ohm and RC is 6 ohm. So substitute all the values and you will get 6 ohm. So you can write RAB is 6 ohm. Next RBC, here RBC is here, so substitute all the values as per the formula and you will get 12 ohm. And similarly for RCA, the formula is RB plus RC plus RA divided by RB. So you can substitute all the values in the formula and you will get RCA is 18 ohm. So RCA is 18 ohms over here. Next, you are going to find the equivalent resistance for all the parallel resistances. So you need to draw this delta connected into this delta. How you need to do here is this one is like this. Okay, here A, B, C, that is the 6 ohm, 9 ohm and the 12 ohms are similar to here, 6 ohms, 9 ohms and 12 ohms. Next, this resistance 6 ohm, 18 ohms and 12 ohms. This resistance comes from this delta. Here it is 6 ohm, 18 ohms and 12 ohms. Comes from this delta, and this delta comes from the star. Okay, this inner star is converted into delta, and the delta circuits, that is the delta parameter resistances, are made or connected in the outer delta like this. So you can see these two resistance are parallel, and these two resistance are parallel, and these two resistance are parallel. So what we are going to do is find the equivalent resistance for this two and substitute a single resistance in the branch AB. Similarly, for this also you are going to find the equivalent resistance, and you have to substitute a single resistance value for the branch AC. Similarly, also you are going to substitute a single resistance for the branch BC. So on doing so, you will get a single delta connected circuit. Here the branch AB has a resistance of 3 ohm, and the branch AC has a resistance of 6 ohm, and branch BC has a resistance of 6 ohm. So this delta is to be converted again to star connected. So this is the delta. Here the delta values are 3 ohm, 6 ohm and another 6 ohm. So this delta connection is converted back into star connection. So to convert the delta into star, you are having a formula RA is equal to RAB RCA divided by RAB plus RBC plus RCA. So substitute all the values. Here RAB is 3 ohm, RCA is 6 ohms, and RAB is 3 ohms, and RAC is 6 ohm, and RBC is 6 ohm. So substitute all the values. You will get RA is 1.2 ohm. Here this is RA and this one is 1.2 ohm. And similarly for RB and RC, you can substitute the values from the delta connection into the formula, and you can find RB and RC. RB value is 1.2 ohm and RC value is 2.4 ohm. So substitute this value in the star circuit. Next, the question is you need to find the equivalent resistance across the point A and B. So the resistance between A and B you need to find. So to do this, you can see the resistance RA and RB are in series. You need to leave this resistance RC, because in question they are asked the effective resistance across the A point and the B point. So you need not to consider the C point and leave this point. So the effective resistance across AB you need to find RA plus RB. So if you leave this point, then the resistance RA and RB is in series. So if the resistance are in series, you need to just add up the two values. So 1.2 ohms plus 1.2 ohms give you a value of 2.4 ohms. This is the third question. Here, using star to delta conversion technique, obtain effective resistance across AB for the figure given. So this is the figure given in the circuit, and in this circuit you need to find the total effective resistance across the point A and B. The parallel combination of 3 ohm and 6 ohm between the C and D point. You can see this is the C point and this is the D point. So at first these two resistors are in parallel. So you need to convert this two resistance into a single resistance. So since it is in parallel, you can convert like this: 1 by 3 divided by 1 by 6 whole inverse. If you do this, the formula, that is the equation, will be like this: 3 into 6 divided by 3 plus 6, which will be equivalent to 2 ohms. So this is being summed up, that is this is being converted, that is the parallel resistance are being converted, and its value is 2 ohm. So you need to redraw the circuit. Here the same thing, the 2 ohm is present. Next, this two resistances are being paralleled and it is 2 ohm. Next, everything, that is the 10 ohm is same and the other 24 ohm is the same. Next, you can see this two resistors are in series. So you can directly sum up these two resistors, which is nothing but 12 ohms. Okay, if you add these two resistors, you can get 12 ohms. In the next step, you need to convert this circuit. You can check these two resistors are now in parallel. So what you can do here is you can use the formula 1 by 12 ohm plus 1 by 24 ohm whole inverse. Okay, if you do this, you will get 24 into 12 divided by 24 plus 12, which will be equivalent to 8 ohms. So here the 2 ohms will be same, and this parallel combination is converted into a single resistance, which is 8 ohms. Now these two resistors are in series, so this series combination of resistance can be added. So 8 plus 2 is nothing but 10 ohms. So this is the fourth problem. Deduce the circuit to its effective resistance between A and B using star delta conversion techniques to simplify the circuit. So this is the circuit. You need to find the effective resistance across the point A and B. So first you need to look into the circuit very deep. Here the circuit in this A, C, D, this will be like a delta. How I say this one is a delta is, you need to redraw the circuit. You can see A to C, this is one point, A to C, and again A to D, there is another one resistance, A to D, and from D to C there is another one resistance. Okay, so this represents the delta combination. So you can use the delta to star conversion to convert this delta position into star position first. So convert the delta connected, that is the 20 ohm, 20 ohm and 60 ohm into star connection. To do this, you know the formula RA is equal to RAB RCA divided by RAB plus RBC plus RCA. So substitute all the values, you will get 4 ohms. Next find RB, it will be 12 ohms, and then find RC, it will be another 12 ohms. Okay, if you redraw the circuit, you will get the star in this position. Okay, the resistance RA is 4 ohm and RB and RC are 12 ohm. So you get this star connected circuit like this. Now to find the effective resistance across the points A and B, you need to look into the circuit. First you can see these two resistance are in series. Next these two resistance are in series. After that these two resistance, that is the branch, this branch and this branch are in parallel. After these two parallel branches, here one resistance is in series with the two parallel branches. So this effective circuit can be easily be converted. To do so, you can see the summation of this two will give you 30 ohms. Okay, so similarly the summation of this 12 ohms plus 8 ohms will give you 20 ohms. So the effective resistance across this branch is 30 ohms and the effective resistance across this branch is 20 ohms. So you can see this 4 ohm resistor is in series with the parallel combination of 30 ohm resistor and a 20 ohm resistor. So you can directly write the formula in a such a way that the 4 ohm plus 1 divided by 30 plus 1 divided by 20 whole inverse, which is nothing but 4 plus 1 divided by 30 plus 1 divided by 20 inverse. Okay, so this will give you a value of 16 ohms. Okay, how this 30 comes here is you need to add these two values, which is nothing but 30 ohms. Okay, similarly for this branch you need to add these two values, you will get 20 ohms. Okay, so these two branches are in parallel and this one is in series. Get this, which is 4 ohm plus 1 divided by 30 plus 1 divided by 20, which will be whole inverse, and the effective resistance will be 16 ohm, which will present across the points A and B. Thank you.